Our planet is facing a critical challenge. Carbon dioxide emissions are rising. These emissions are a major contributor to climate change. We need to find new ways to create energy. Sustainable fuels are a vital part of the solution. Fossil fuels have powered our world for centuries, but burning fossil fuels releases harmful greenhouse gases. These gases trap heat in the atmosphere. This leads to global warming and its devastating effects. We must transition away from fossil fuels. Sustainable fuels offer a cleaner alternative. These fuels are produced from renewable sources. They release fewer emissions. This can help us combat climate change. Sustainable fuels are essential for a healthier planet. We must act urgently. Time is running out to address this global crisis. The development and adoption of sustainable fuel is not just an option. It is a necessity. Our planet's future depends on it. Scientists are exploring innovative ways to produce sustainable fuels. One promising approach is CO2 Electr Reduction. This process uses electricity to convert carbon dioxide into valuable chemicals and fuels. It offers a way to utilize CO2, a greenhouse gas. CO2 Electr Reduction mimics nature's process of photosynthesis. Plants use sunlight to convert CO2 and water into sugars. Similarly, this technology uses electricity to power the conversion of CO2 into useful products. This process can create a closed carbon loop. In this process, electricity is passed through an electrochemical cell. The cell contains a cathode and a node and an electrolyte. CO2 is fed into the cell. At the cathode, CO2 molecules are reduced. This means they gain electrons. The reduction of CO2 leads to the formation of various products. These can include carbon monoxide, formic acid, methane, and even more complex hydrocarbons. The specific products depend on several factors, including the catalyst used, the applied voltage, and the electrolyte composition. Catalysts are essential for CO2 Electr Reduction. They accelerate the chemical reactions involved. Cobalt-based catalysts have emerged as promising candidates for this process. These catalysts exhibit high activity and selectivity for CO2 conversion. Researchers have developed various cobalt-based catalysts. These include cobalt oxide, cobalt carbonate, and cobalt phosphate. These catalysts are synthesized through different methods. These methods ensure the catalysts have a high surface area. One common method involves precipitation. In this method, a cobalt salt solution is mixed with a precipitating agent. This leads to the formation of cobalt-based particles. The particles are then calcined at high temperatures to obtain the desired catalyst. Another method utilizes electrochemical deposition. In this technique, a cobalt salt solution is used as the electrolyte. A voltage is applied between two electrodes immersed in the solution. Cobalt ions are reduced at the cathode, forming a thin film of cobalt-based catalyst. Among the various cobalt catalysts, cobalt oxide has garnered significant attention. This is due to its unique properties that make it highly effective for CO2 Electr Reduction. Cobalt oxide has a spinel structure, providing active sites for CO2 adsorption and activation. It can be deposited onto various electrode materials. One common approach is using gas diffusion electrodes. These provide a large surface area for catalyst loading and efficient CO2 transport. Section 5, Molecular Interaction of CO2 and Co3O4. The interaction between CO2 and Co3O4 is crucial for understanding the mechanism of CO2 Electr Reduction. When CO2 molecules come into contact with the Co3O4 surface, they adsorb onto the active sites. This adsorption process is facilitated by the oxygen vacancies and the electronic properties of Co3O4. Upon adsorption, the CO2 molecule undergoes activation. This means that the bonds within the CO2 molecule are weakened. This weakening of bonds is essential for facilitating further reactions. The activation of CO2 on the Co3O4 surface is attributed to the transfer of electrons. Co3O4 donates electrons to the CO2 molecule, resulting in the formation of a negatively charged CO2 species. This negatively charged species is more reactive and prone to further reduction. Section 6. The magic of CC coupling. The conversion of CO2 into valuable hydrocarbons requires the formation of carbon-carbon CC bonds. This process, known as CC coupling, is a crucial step in CO2 Electr Reduction. Cobalt-based catalysts, particularly Co304, have shown remarkable activity in promoting CC coupling. CC coupling on Co304 surfaces is believed to occur through a complex mechanism involving adsorbed CO intermediates. When CO2 is reduced on Co304, it forms CO, which can adsorb onto neighboring active sites. The adsorbed CO molecules then undergo coupling reactions, leading to the formation of CC bonds. The exact mechanism of CC coupling is still under investigation, but it is thought to involve the formation of surface-bound intermediates. The ability of Co304 to promote CC coupling is attributed to its unique electronic structure and the presence of oxygen vacancies. These features create favorable conditions for CO adsorption and facilitate the interaction between adsorbed CO molecules, leading to CC bond formation. Section 7. Anderson-Schultz Flory distribution and chain growth. The product distribution in CO2 Electr Reduction is often described by the Anderson-Schultz Flory ASF distribution. The ASF distribution is characterized by a chain growth probability, alpha. A higher alpha value indicates a greater tendency for chain growth. Co304 exhibits a moderate chain growth probability, resulting in hydrocarbons from methane to heptane. Section 9. Real-world applications and future prospects. The development of efficient and stable CO2 Electr Reduction technologies has the potential to revolutionize various industries. By converting CO2 into valuable chemicals and fuels, we can mitigate greenhouse gas emissions and transition towards a more sustainable future. One promising application of CO2 Electr Reduction is in the production of synthetic fuels. These fuels, also known as electrofuels, can be used as drop-in replacements for gasoline, diesel and jet fuel, offering a cleaner alternative to fossil fuels. CO2 Electr Reduction can also be used to produce valuable chemicals such as ethylene, propylene and ethanol. These chemicals are essential building blocks for various products, including plastics, fertilizers and pharmaceuticals. The scalability of CO2 Electr Reduction technology is a critical factor for its widespread adoption. While significant progress has been made in developing laboratory-scale prototypes, further research and development are needed to scale up the technology for industrial applications. Section 10. The road ahead, scaling up for a sustainable future. Scaling up CO2 Electr Reduction technology presents both challenges and opportunities. One of the main challenges is the development of highly active, selective and stable catalysts that can operate at industrial scales. Another challenge is the design of efficient and cost-effective electrolyzers that can handle large volumes of CO2 and electricity. Optimizing the operating conditions such as temperature, pressure and electrolyte composition is crucial for achieving high conversion rates and energy efficiencies. Despite these challenges, the potential benefits of CO2 Electr Reduction are too significant to ignore. By investing in research and development, we can overcome these hurdles and unlock the full potential of this transformative technology. Governments, industries and research institutions must work together to accelerate the development and deployment of CO2 Electr Reduction technologies. This includes providing funding, fostering collaborations, and creating supportive policies. Section 11. A call to action investing in our planet's future. The time to act is now. Climate change is a pressing global challenge that requires immediate attention. CO2 Electr Reduction offers a promising pathway to mitigate greenhouse gas emissions and transition towards a more sustainable future. By investing in CO2 Electr Reduction technologies, we are investing in the health of our planet and the well-being of future generations. Let us embrace this opportunity to create a cleaner, greener, and more sustainable world. Together, we can make a difference. By supporting research, advocating for sustainable policies, and making conscious choices in our daily lives, we can drive the transition towards a carbon-neutral future. The future of our planet depends on the actions we take today. Let us rise to the challenge and create a world where sustainable technologies such as CO2 Electr Reduction play a central role in powering our societies.